Welcome everybody. We're going to talk about multiple stereocenters in a molecule. We talked about what happens if you have one. You can have a mirror image if it's chiral, and you can have enantiomers. What happens if you have more than one? Let's look at it. Let's take an example. When you have multiple stereocenters, it means that you have more than one chiral center in a molecule. All right. So an example would be a molecule, let's say, that has CH3, CHCl, and then CHOH, and CHO. So, well, what are the ways in which we can write this? Well, this is just a molecule that's written as a condensed formula. You can see that over here, these two carbons have the possibility of being chiral centers. So what are the possibilities for this molecule? Let's analyze that, okay? Let me just draw a line diagram for that because sometimes it's easier to see it. So here is CHO, so CHO. And then here is a hydroxyl. So the hydroxyl can be either out or in. So chlorine, let's say we will put that in a red color or pink, and the hydroxyl, let's say we put it in a yellow color. That's going to be pretty much your molecule. This is a methyl group here at the bottom. What are the possibilities? The CHO obviously has a plane of symmetry on this carbon because it's sp2. So that's achiral. CH3, there are 3 hydrogens, right? Even if you have just 2 hydrogens, it will become achiral. So that's achiral. So both these are achiral. But over here, you have a possibility for a chiral center because you have 4 different things. You don't see the hydrogen, but there is a hydrogen right here. And a hydrogen right here, 4 different things. So there are 2 chiral centers in here. Let's see how we can represent them. So if you have 2 chiral centers, the formula to find the number of chiral centers in a molecule is 2 to the n, where n is the number of chiral centers. So in this case, you have 2 chiral centers. So you have 2 to the 2, that's 4 stereoisomers. Those are the possibilities. So how are you going to draw them? Well, you can have the hydroxyl and the chloride both on the same side, or on, let's say in this case, because it's a perspective diagram, we have to show them with wedges and dashes. Both on the wedges, both on dashes, one on a wedge, one on a dash, or one on this on a dash, that on a wedge. Are there any other iterations possible for distributing these molecules in different spatial arrangements? That's it, right? We covered it all because you only have 2 chiral centers. So let's draw those out. So 4 stereoisomers, let's draw them out. So let's draw one where both these groups are coming at you, and another one where both of them are going away from you. You can draw one where you have one out coming towards you and one away from you. You can draw another one where it's in the opposite configuration of the previous one. Let's do it. Okay, so and here's going to be our chiral centers, and I'm going to put 4 carbon, 1, 2, 3, and the 4th carbon is a methyl. We'll put it in a blue color. And over here, the way it's the model is, if blue is the methyl and the green here is the double bond, then you would have in this molecule the hydroxyl coming toward you and the chloride coming towards you. So for you, those are both going to be on a wedge. I have to be careful when I'm drawing this because for me, I am actually part of the mirror image. So it's the opposite for me, but I'm drawing what you can see. So that's one. The next one here is going to be So that's A, let's say B, C, and D. Same thing, the COH, and you have a methyl, and second and third carbon have chiral centers, and over here we're going to draw the other one where you have both of them going away from you, right? So this is, the hydrogens are coming toward you, the groups are going away from you. So let's draw that out. So here's your hydroxyl, and here is your chlorine. Let's look at another possibility where you can have the hydroxyl coming toward you and the chlorine going away from you. So here's your carbonyl, and we have your methyl at the very end. So this is going to be hydroxyl coming towards you. And then your chloride going away from you. Now, the last one would be where we're going to switch. And if you can think of anything else, let me know. Any other possibility. So here we have our methyl at the very end, a little tail wagging out there. Swish, swish, swish. And then you have the hydroxyl going away from you, chlorine coming towards you. So the chlorine coming towards you, hydroxyl going away from you. Hydrogen is coming towards you on this one. So over here, hydroxyl going away from you. And chlorine's coming toward you. So those are pretty much all of the possibilities for the spatial orientation of two different groups on this chain. Same side, opposite side, and staggered, left, right, and right, left. All right. Now, another important thing to recognize in this molecule would be the relationship. What's the relationship between these molecules? How are they related? Are they first cousins, second cousins, or distant, uncle? Let's look at it. This guy and this guy are these two. And you can, if I hold this guy and this guy, well, it's not obvious when I hold it like that. Let me hold it up like this. So let's see what the relationship is. What do you think these guys are? Yeah, what do you think is the relationship between these guys? They are perfect mirror images. Okay, so these are enantiomers. Because if you take each of these molecules, it doesn't have a mirror plane of symmetry. Therefore, individually, they are chiral. They have all of the groups in the same places, and the connectivity is the same. So they are not constitutional isomers. They are only different in the spatial arrangement of these groups. These two are on the right-hand side, and these two are on the left-hand side. So these only differ in spatial orientation, which makes them stereoisomers. Stereoisomers that are mirror images, and they're non-superimposable mirror images, are called enantiomers. All right, so these two are mirror images. Let's look at C and D. Here's John holding them up for you. And you can see that over here, these two groups are reflected as though on a mirror on this molecule, and they're in the exact opposite orientation. Okay, so they are mirror images, and you can see they are non-superimposable mirror images. If you put them one on top of the other like this, they won't superimpose because of the different spatial orientations. Therefore, non-superimposable mirror images are enantiomers. That's great. So we established A and B are enantiomers, C and D are enantiomers. But what about A and C, A and D? or B and C, B and D. What's the relationship there? Let's look at it. So let's take A, and well, here is a molecule. The top here is the same. The bottom is inverted. So this is a reflection, this is not. This is the same, this is inverted. Therefore, it's not a mirror image. But at the same time, they're both stereoisomers because everything is connected to the exact same things in the exact same order. So the molecule is the same except for the spatial orientation of these two groups. That's the only difference. Okay? So these are stereoisomers, but they're not mirror images. We have a special name for them. That's diastereomers. All right? So diastereomers are stereoisomers that are not mirror images. So stereoisomers that are not enantiomers can be diastereomers over here. All right, and it would be the same with A and D. As you can see with A and D, you can see that these are on the same side, these are on the opposite sides. Okay, so therefore A and C and A and D are diastereomers. So if you're not a mirror image and you're a stereoisomer, you are then a diastereomer. So you can have multiple diastereomers, but you can only have one mirror image. Just like when you are in the mirror, you can only have one reflection of you, right? You can't have different reflections doing different things. So you'll have everything's opposite, then you're a mirror image. But if some are opposite, some are same, then you're a diastereomer because you're not a mirror image. All right? Let's look at B. We have B here. And again, this is B and C. You can see same deal one more time. This has got both on the same side. They're opposite. Same here with these. They're opposite. All right. So B can only have one mirror image, which is A. All the others will be diastereomers for that. And it will be the same for C. C would only have a mirror image with D. So those are enantiomers. All the others for this molecule would be diastereomers, and same with D. All right, so you can have a lot of diastereomers depending on how many stereocenters you have, but only one of those would be an enantiomer pair for a stereoisomer. All right, you can have multiple enantiomer pairs, but if you take one molecule, you can only have one reflection, and so one enantiomer. All the others would be diastereomers for that molecule. And we'll talk about meso, but for right now, just remember, if you have multiple stereocenters, you can have multiple stereoisomers. One of them would be an enantiomer for a particular stereoisomer. All the others would be diastereomers. All right. Thank you. Thank you, John.
Stereo.
All right, so let's draw, and let me write that down. A, B, and C, D pairs are enantiomers. And all the others, A, C would be the same as CA, A, D, and then also B, C, and BD pairs are diastereomers. Okay, one very important statement. Stereoisomers that are not enantiomers are diastereomers. Stereoisomers that are not mirror images, which means not enantiomers, are diastereomers. All right. Let's draw these out. This is also a practice for you to draw them out in different projections or different types of diagrams. This is called the perspective diagram. All of these. This is very easy over here to do RNS. This is the perfect place to do RNS. All right, so let's look at the RNS. Perspective diagrams are the best place to actually nail these things and say whether it's RNS. So let's put our hydrogens here. The hydrogens are going in here, so this would be the best one to do. And if it's a wedge and goes to an R, then obviously they are inverted. If it's an R, it will go to an S, it will go to an R when it's reflected. Let's do this. 1, so this is chiral center number 1. This is connected to a oxygen, these are carbon, so this is obviously number 1. Between this carbon and this carbon, this is connected to a chlorine. Obviously people connected to these heavyweights obviously get higher priority, they get front row seats and all. So let's do this. So here we are going in this direction, so that is going to be an S. And let's look at the other one over here. On this chiral center, you have chlorine. Obviously that's going to be way heavier than anything else, and then you would have this carbon and this carbon then to contend with to see which is higher in priority. This one's connected to an oxygen, and so this one would have higher priority, and this would be 3. 4 would be obviously the hydrogen in both cases, and this is going in this direction, and that would be an S. So we have 2 S's here, which means when you reflect them, S is always reflected as an R. And over here, this is the same as this. This is a retention, and here's an inversion. And here, from here, this is a inversion, and this is a retention. So we've nailed our R and S right there. What I'd like to do is use the rest of the time here to draw different perspectives of these same molecules. That's really important then to go from one type of diagram to another. For example, if you want to go from perspective diagram to fissure, we can go through a Newman, which will make it a lot easier to draw the fissure, because then you would see exactly where these groups are. So that's kind of a fail-safe way or a foolproof way of getting to a fissure, is to go through a Newman. And to go through a Newman, you'd have to draw it just like your butanes. So you are going to look through C2, C3 and draw it out like this. All right, so let's draw these out here. So what's going to be on the wedge here would be coming to the right hand side. All right, let's draw it out. Newman is going to be looking through carbon 2, 3, because that's where your chiral centers are, so it makes sense to look at it through there. So if you keep your eye here, you're going to hit this carbon, which is a dot, and that dot is going to have a hydroxyl and a CHO going up, and the hydrogen on the opposite side of the OH. Looking through this, here you're going to look through this carbon, but when you look at it head on like that, you don't see that carbon. So we're going to draw a circle for that back carbon. And so the circle there would have the chlorine on the same side as the hydroxyl. And I'll put the blue, the methyl in blue. All right. Now this is a mirror image of that, which means these two are going to be on the opposite side. So let's draw that out. So for the front carbon here, so again looking at it like this, you're going to hit that dot, and that's your circle. So for the dot carbon, you would have your hydroxyl on the opposite side of this. Well, we won't change the others, only this is being reflected. Now over here, you would have the back carbon as a circle, this carbon, and you would have your chlorine on the same side as the hydroxyl. Hydrogen on the opposite side, because that's going to be on the wedge there, and your methyl. Let's do the same thing over here. Let's look through the same C2, C3, because we're going to compare these molecules. We're going to look at the same perspective for each of them. So here, again, you have a wedge. and it's the same as this. So it'll be on the same side as that oxygen, hydrogen, and you are going to, sorry, I'm holding up the wrong model here. So this is for this one. You can see they're both over here, and this is going to be for this one. They are on opposite sides. So if the hydroxyl is on this side, then your chlorine would be on the opposite side. And you can see that here too. One's a wedge, one's a dash. The way it's drawn, because we're drawing exactly what we're seeing without rotating any of this. So hydroxyl and chlorine would be on opposite sides here. And let's look at the last one over here. So here too, you are going to have your hydroxyl and chlorine on opposite sides when you're going to look at it through here. All right, so chlorine is going to come on this side. Let's draw that out, and hydroxyl will be going on this side. So that's the top one. And then you will draw your hydroxyl here and your hydrogen here. And let's do the back carbon, which is going to be the circle here. And on that, you're going to put your chlorine on the opposite side of the hydroxyl, because we're drawing it just the way that it is. We're not doing any rotation there. This is a rhodomer that we're drawing. All right, so you can see over here, it's a lot easier now to see whether it's going to be mirror images or not. This is a perfect reflection of that. So these are enantiomers. This is a perfect reflection of this. So these two are enantiomers. And that's what we have said over here as well. These, as you can see, this is reflected and this is not. So one is inverted, this is retention, this is inversion, right? So unless both are inverted, they're not enantiomers. Therefore, these are stereoisomers because they have the exact same molecular formula, connectivity, everything's the same, the spatial orientation's different. And they are not opposite. If they were opposite, you'd call them enantiomers. But because you have stereoisomers that are not mirror images, are called diastereomers. And here we can see that because they're right next to each other, but we have other pairs as well, this and this, this and this, this and this, this and this. All right, so we know what enantiomers are, we know what diastereomers are, we know RNS. We're going to do one more thing that you haven't done before. Let's draw a Fisher projection. What do they mean by Fisher projections? Let's look at it. A Fisher projection, it means it's just a way of drawing a molecule so the chiral centers become very prominent and obvious. Because if you draw it out like this, you have to go check each one, and it's not very obvious. But here, in a Fisher projection, what they do is they say, okay, this is your longest carbon chain. Put it on the vertical line like this, line, the longest carbon chain. Put the most oxidized carbon on top so that people know, okay, you're going to draw this and not this. So you fix that, what's head and what's tail. Now, you say that whatever is on the horizontal lines are coming towards you. And you can see that that's correct. And whatever is on the vertical line is going away from you. So it's a three-dimensional diagram implied by a 2D diagram. So one, let me just write that down. Longest carbon chain on vertical axis. Most oxidized carbon on top. 3. This means vertical lines are dashes. Horizontal lines are wedges. So because it's actually a 3D diagram. One more thing. Let's say you have A, B, C, D, a chiral center here. Okay, so these are going for you, going away from you. These are C and D are coming towards you. Now you can do two things. You can rotate it 90 degrees or you can rotate it 180 degrees. Okay, so 90 or 180. If you do 180, A and B are going to be flipped, but they're still going to be going away from you. C and D are going to be flipped. Whereas when you do a 90, your wedges become dashes and your dashes become wedges, which means it's a reflection, which means it's an enantiomer. Okay, so this is allowed, this is disallowed, this is going to be a mirror image, that's what it means. So this is going to go like this, D and C. These are enantiomers, so let's call this 1, 2, and 3. 1 is the same as 2. 1 and 3 are enantiomers. 1 is not the same as 3, they are enantiomers. All right, so let's draw out a Fisher projection for this. You can do it right away, but to make it like foolproof or what may call error proof, it might actually help you to draw the molecule with the methyl and the CHO on the same side, because you're going to put the vertical line as the carbon chain and that's going to go away from you. That means this and this should both go away from you. Why don't you put that in the same place in the same at the same time and then draw it out. So we want to draw a Fisher projection. That means we want to draw it like this, which means you're going to go from a Newman projection that is like this. So you had it like this, then you have to put the carbons on the same vertical line, you see. So if you want to make sure that you don't make any mistakes, the best thing to do would be to put the methyl group over here and redraw it, and then you know what's going to be on the right hand side or left hand side of that molecule, and there would be absolutely no ambiguity about it, right? All right, let's do it. So let's draw out the eclipse Newman for all of them. We're going to keep the front carbon the same and just rotate the back carbon, all of the back carbons 180 degrees. So when you rotate the back carbon 180, the chlorine will be here, the hydrogen will be here, and the methyl will be here, for the example. Okay, so let's do it. So I'm going to draw it right here, see eclipsed. Keep the front the same. Back carbon is going to be rotated, methyl goes up, and chlorine and hydrogen are going to come over here. Do the same thing here, eclipsed by rotating the back carbon to align with the CHO, because that's what the Fisher projection says. Longest chain is vertical, and vertical lines should always be going away from you, and so they should be in the same direction. So I'm going to put all the carbons facing the same way. So this is going to be 1, this is for A, this is for B. They're the same molecule, so I'm not going to even label it different. So methyl goes up, and then over here everything goes 180, so you don't really have to even twist your brain around it. It's just everything goes to the opposite side because you're doing 180. So this is going to be B, and over here you're going to do, so that is going to be B, which is taking this and drawing it like that. Okay. So if it is on the same side in the staggered, they'll become opposite side in the eclipsed. So we'll keep the front the same as we said before multiple times. Sorry for repeating everything. All right, so over here, you're going to take this methyl, go up here. So the methyl is going to be pointing up. Everything goes 180. Chlorine comes over here. Hydrogen comes over here. Good, that's C. D, you're going to have a, I'll draw it over here, guys. So you'll have a hydroxyl in this direction, and the back carbon, if you rotate it like this, everything's going to go 180 degrees, and your methyl is going to be up here parallel to this, and chlorine goes over here, and hydrogen would go 180 parallel to this. So opposite side on the staggered will become same side on the eclipsed. Same side on the staggered will become opposite side on the eclipsed. Okay, all right, so we got all four of this. Now, and again, it's really easy once you draw the eclipse also to see that these two are enantiomers, and these two are enantiomers, and these are, all the others are diastereomers. This is now then going to be very helpful. So over here, I'm sorry, I forgot to hold the models. Let's look at it again. So I'm going to make the methyl and the CHO on the same side, and you can see that these are your Newman projections. All right, for eclipsed. All right, now you can take this and draw the Newman from here really easily. So over here, you take this, you drew this. All you have to do is draw it out like this. You're seeing it like belly up. Okay, so your CHO is up, CH3 is at the bottom, and here are your hydroxyl and chlorine. All right, let's draw this out. So I'm going to put the vertical line like this, and the methyl. So that's your vertical line, and that's your CH3, and here is your aldehyde. Now you have two chiral centers, and those would be your chiral centers. And over here, you can see, if you draw this out and you're just looking at it belly up like this, you're drawing the hydroxyl and the chlorine on opposite sides. All right. So this is another way to check if you did this right. Let's go 1, and then this is oxygen, this is a carbon, this is chlorine, this is oxygen. So this is going to be, with the hydrogen out, this is going to be S. So we did get that right. Here's, for this chiral center, this is, obviously this is number 4. 1, and between this carbon which has hydroxyl and aldehyde, whereas this has just got a methyl, this would be higher priority. And this is going to be 3. So going in this direction, with this being on a horizontal line, which means it's coming towards you, that's going to be then also an S. So you can see S, S, and this is also, sorry, S, S. So we did do something right. All right, let's do the same thing over here and draw the same thing. So here is your eclipse Newman, sorry, and so you stretch it out. This is going to be your Fisher. All right, let's draw it out. So you're going to look at it like this, belly up. These are going inside. CH3, and this is going to put your hydroxyl. You're seeing it on this side, and your chlorine is going to be on the opposite side, and this is your CHO on the same direction as your methyl. your chlorine will be on the opposite side. And this is even more obvious now why these two are enantiomers. Okay, all right, let's do the same thing over here. Look at it, belly up, going down like this, methyl group is going away from you, vertical lines are going away from you, horizontal lines are going toward you. And here's your chiral center on this side. Put it on the same side that you see, and the chlorine will be on the exact same side. If you do this, then really there's no ambiguity about where should it be, how should I twist it, and all of that. Just do a Newman staggered, do a Newman eclipse, and the groups that are on the same side should become coming on the same side here. All right. One more here. So you take this and you look at it. So same thing. You're going to do this and methyl down. So you're going to look at it like this, and you're going to draw this out. Sorry, I don't have too much space. I'm going to kind of crimp it in here. And here's your CHO. And sorry, this is your hydrogen and your hydroxyl, and on the same side is your chlorine and your hydrogen. All right. If you want, you can make sure that these are correct by doing an R&S test. So this is going to be 1, 2, 3, and so this is coming out, and so therefore this is an R. One. So on the fissure, it would be the opposite of what you have on your Kroninger-Prelog rule, because always hydrogen will be on a wedge, because hydrogen, you know, the carbons would be on the vertical line, so these hydrogens would be on a wedge. So the Kroninger-Prelog rule says to put hydrogen on a dash away from you, but the way we've drawn it, it's coming on a wedge towards you. So clockwise for you would be with the hydrogen on a wedge would be S. Counterclockwise with the hydrogen on a wedge would be R. Okay, there you go. All right, so those are some very important points to remember, that enantiomers are non-superimposable mirror images, and diastereomers are stereoisomers that are not mirror images. Just in summary, I'd like to say that there are many ways in which you can draw a molecule in 3D, and one of them would be the perspective diagram, the other one would be the Newman, and then we would also have a Fisher projection. So 3 ways of drawing them, and we've tried to incorporate all of them in this video. All right, so these are your Fisher projections. Now, in the fissure, you also have to make sure that you extend it where group 4 is actually on a wedge, because in all of these cases, if you're going to put the carbon chain on the vertical line like the rule says, then your hydrogen is definitely going to be on the horizontal line, and you could then like do a rotation if you'd like and do it, or you could mentally think that it's going to be the opposite of that. All right, therefore what it means is, and I will write this here, if your group number 4 is on a wedge, then 1, 2, and 3 going clockwise would be an S. If your group number 4 is on a wedge and 1, 2, and 3 is going counterclockwise, that would be an R. Okay, so if you keep this in mind here, it would make it a lot easier when you're doing a fissure. On a fissure, if it's going clockwise, that would be an S. If it's going counterclockwise, it is going to be an R, because hydrogen again is coming out at you coming out at you on that side on a wedge. All right, so make sure that you remember that when you're doing R and S for all of these things. For example, this is going to be an R, and over here, this is going also same direction, is also going to be an R. All right, so I hope we did a lot of practice for you. We'll do some practice problems when we come back, guys. So take your book and just flip to the end of chapter problems, or go online. There are tons of online practice problems. Do them and let me know if you have any questions. Talk to you soon. Bye.